A network is built on a physical constraint, but it operates through a dynamic layer of software. Every time data moves, it is navigating two simultaneous architectures at once. The first is the physical topology, known in the Open Systems Interconnection model as Layer 1. This is the rigid, hardware-centric installation of your infrastructure. It dictates the exact geographic placement of your server nodes, workstations, and the tangible copper or fiber cables that link them together. The second is the logical topology, or Layer 2. This is the conceptual map of how data signals actually traverse that hardware. Layer 2 defines the protocols of data flow, and it operates entirely independent of how the physical cables are arranged in the walls. The primary task of a network engineer is to master the tension between these two layers, pushing logical data delivery to its absolute limit while staying within the boundaries of a static physical constraint. To see how those physical limits shape data, we start with the foundational problem of early networking, connecting multiple nodes using the absolute minimum amount of hardware. The initial solution was the bus topology. In a physical bus, all devices attach linearly to a single central backbone cable. At Layer 1, any electrical signal transmitted by a node will travel outward in both directions. Because signals bounce when they hit the end of a wire, precise physical terminators are required at both ends to absorb the voltage and prevent corrupted reflections. But the bus design immediately hits a Layer 2 limitation. Because all nodes share the exact same medium, they rely on an access protocol called CSMA CD. A node listens to the wire, and if it sounds clear, it transmits. If two nodes transmit at the exact same millisecond, their signals overlap and corrupt each other. This is a data collision. When a collision is detected, the CSMA CD backoff mechanism engages. Both nodes immediately halt their transmission. Wait for a completely random interval of milliseconds, and then try again. This model fails under modern scaling. As you add more devices to a shared bus, the mathematical probability of collisions rises exponentially, dragging bandwidth to a crawl. Worse, a single physical break anywhere on that backbone cable triggers a total network failure. Engineers bypass the collision problem by reconfiguring the backbone into a closed physical loop, the ring topology. Instead of broadcasting raw voltage in both directions, signals travel in a single unidirectional path. Each node receives the data and acts as an active repeater, regenerating the signal's strength before passing it along. This physical loop enables a highly controlled Layer 2 protocol known as token passing. A specialized bit pattern, the token, constantly circulates the ring. A device is only permitted to transmit data if it is actively holding that token. This creates deterministic access. Because only one device can physically speak at a time, collisions drop to zero. Every device on the network is guaranteed equal bandwidth access, resulting in perfectly consistent, predictable latency. That rigid predictability makes ring topologies ideal for industrial automation and utility management. When monitoring pipelines or factory floors, engineers require precise data telemetry, where a signal takes the exact same amount of time to travel, every time. Yet the ring remains physically fragile. If one node fails or a single cable is cut, the loop breaks. To maintain uptime, these networks require a secondary, redundant ring to allow the data to wrap backward and self-heal the path, doubling the physical cost. Modern enterprise networks solve the localized fault problem by breaking the loop entirely. In a Star Topology, every node has its own dedicated physical cable connecting back to a central aggregation device. If one workstation's cable breaks, only that workstation goes offline. However, physical layout does not dictate logical behavior. If that central device is an older network hub, the network is physically a star, but operates as a logical bus. A hub simply takes an incoming electrical signal and duplicates it across all other ports, blasting that data to every machine and guaranteeing heavy collisions. The modern leap in performance relies on micro-segmentation. By replacing the hub with a network switch, the logical landscape shifts. The switch reads the specific hardware address of an incoming packet and creates a temporary, isolated, point-to-point connection exclusively with the destination node. By isolating every conversation, the switch eliminates the risk of collisions. Devices can now send and receive data simultaneously in full duplex mode. This modularity allows the star to scale hierarchically, connecting smaller switches to larger core distribution switches to form the extended star networks used in multi-floor corporate campuses. The engineering trade-off is clear. You gain perfect fault isolation and micro-segmentation, but you pay for it with incredibly dense, expensive cable runs, and you concentrate all your risk into the core switch. If the center fails, the entire network goes dark. To strip away that single point of failure, you have to build extreme physical redundancy. In a full mesh topology, every single node connects directly via its own dedicated link to every other node on the network. But full mesh encounters a brutal mathematical barrier. The number of physical links required increases exponentially with each device you add. Connecting 20 nodes requires nearly 200 separate cables. The required hardware ports and capital expenditure quickly scale out of control. The pragmatic compromise is the partial mesh. You only interconnect the mission-critical hardware, like core routing switches, while leaving edge devices on single links. This highly redundant partial mesh forms the backbone of internet service providers and the global internet. In cloud computing data centers, this evolves into the spine leaf model. A massive array of server-facing leaf switches connects directly into a dense row of core spine switches. It's a structured partial mesh, guaranteeing that any virtual server can reach any other server in exactly 2 predictable hops. Absolute physical fault tolerance is economically impossible at scale. Instead, network architects wire an optimized baseline of physical redundancy and rely on dynamic Layer 2 routing protocols to seamlessly redirect data around failed links. This logic over hardware approach dictates network security. In a flat physical topology, an attacker who compromises one endpoint has unobstructed lateral ROSNet to probe and attack every other device on that switch. To stop this, engineers deploy VLANs, or virtual local area networks. By assigning specific switch courts to different logical groups, they can partition a single physical switch into isolated subnetworks. This establishes internal zero-trust barriers, confining data access without running a single new cable. Software-defined networking, or SDN, takes this abstraction to its limit. SDN completely decouples the logical control plane from the physical data-carrying hardware. The wiring simply becomes raw, unconfigured capacity, while all traffic rules and routing paths are scripted centrally in software. The cutting edge of this is intent-based networking. Rather than manually configuring VLANs, administrators set high-level business rules. Artificial intelligence translates those intentions into protocol configurations, constantly reshaping the network's logical overlays in real time to reroute around congestion or isolate a detected threat. Mastering network topology is no longer a matter of drawing static lines between servers. It is the practice of designing raw, resilient physical capacity and commanding a dynamic overlay of code to shape it, secure it, and adapt it to the immediate demands of the information economy.